In example 6, y has a beta distribution with alpha and beta equal to 2, and u is y squared plus 2y plus 1. And we want to find the density function for u. Now, the first thing here is to recognize what's a beta distribution. And we had a lecture on beta distributions. It's part of the series on continuous distributions. If you scroll up, you will see a lecture on beta distributions. Let me remind you of the generic formula for a density function for a beta distribution. So f of y is equal to y to the alpha minus 1, 1 minus y to the beta minus 1. And then we divide that by b of b of alpha beta. And b of alpha beta in turn is capital gamma of alpha, capital gamma of beta over capital gamma of alpha plus beta. So what we have to do is interpret this with alpha and beta equal to 2. So our f sub y of y is equal to, well, if I flip that denominator, I'll have gamma of 2 plus 2, so gamma of 4, divided by gamma of 2 times gamma of 2. And now y to the alpha minus 1 is y to the 1, and 1 minus y to the beta minus 1 is, beta is 2, so beta minus 1 is 1. Now, what is gamma of 4? Gamma of 4, remember there's this relationship between the gamma function and factorials, at least for whole numbers. So gamma of n is equal to n minus 1 factorial. So gamma of 4 is 3 factorial, which is 6. Gamma of 2 is 1 factorial, which is just 1. So those denominators cancel. We get 6 times y times 1 minus y. So 6 times y minus y squared. That's my f sub y of y. And actually, let me now solve for, I've got a function of u is a function of y. I think I need to solve for my inverse function there. So u is h of y, which is y squared plus 2y plus 1. You know what? An easy way to think about that would be as y plus 1 squared. I bet that's going to make it easier to deal with. Now, I want to solve for that in terms of, well, solve for y in terms of u. That's how I get the inverse function. So I'm going to solve for y. Solve for y. So the square root of u is equal to y plus 1. And so y is equal to the square root of u minus 1. So that right there is my h inverse of u. Now, let me remind you of the generic formula for the density function when you use the method of transformations. It says that f sub u of variable u is equal to, well, you start with the density function for y, f sub y, and you plug in h inverse of u, and then you multiply on the derivative, d by du of h inverse of u, and in case that's negative, you want to take its absolute value. So we're going to need to know h inverse of u, and I've already found it, square root of u minus 1. And we're also going to need to know h inverse of u, its derivative. So the derivative there, let's see. Well, maybe I'll just go ahead and plug everything in here. F sub y, there's my f sub y there. So this is 6 times, now it says y, but I have to convert that into u's, to convert that into h inverse of u. So square root of u minus 1. I'm looking at this y minus y squared, but I'm plugging in u square root of u minus 1 for y. So minus the square root of u minus 1 squared. That's going to get a little messy, isn't it? Now, the derivative of h inverse of u is the derivative of the square root of u minus 1. So that's 1 over 2 square roots of u. That's because you can think of that as u to the 1/2. The derivative is 1/2 u to the negative 1/2. And then that minus 1 there, that just goes away when we take a derivative. And we are supposed to take the absolute value of that, but that's already positive, 1 over 2 square roots of u. And now I'm just going to do some algebra to work this out, and hopefully it'll simplify a bit. I don't think it's going to get great, but let's go ahead and see what we can do with this. Oh, the 6 over 2 simplifies a little bit right away. So we get 3 over the square root of u. And now inside the parentheses, I have square root of u minus 1 minus, now if I square out root u minus 1 squared, I'll get u minus 2 root u plus 1 there. And so maybe I can simplify that a little bit more. It's 3 over the square root of u. Root u minus 1 minus u plus 2 root u. Plus 2 root u. And now minus 1 there. And so I guess this will simplify a bit. Equals 3 over root u. And now root u plus 2 root u is 3 root u. Minus 1 minus 1 minus 2 minus root u. Perhaps I can distribute that root u from the outside into the inside. So 3 times 3 minus 2 over root u. Now, u divided by root u is root u. Okay, so that's what I get. And I don't think it's going to get any simpler than that. I think we found our density function. That's f sub u over u. Oh, and the problem reminds us that we should also find the range of possible values for u. So if y, remember for a beta distribution function, y will go from 0 to 1. That's always the range for a beta distribution function. And u, where is u in terms of y? Y is the square root of u minus 1. So u is y plus 1 squared. So u, if it's y plus 1 squared, 0 plus 1 squared is 1. And 1 plus 1 squared is 4. So my range of values for u is from 1 to 4. So that's my density function for u. Kind of ugly there, but I didn't see any way of making it any nicer. I think we're stuck with that. And in the end, it did simplify a little bit, so I guess we have to be happy with that. Let me recap the steps there. First of all, I saw that we had a beta distribution. So I went back and looked up my formula for a beta distribution, which we learned in the lecture on beta distributions. It's quite a long time ago in the chapter on continuous distributions. So just go back and look. You'll see a lecture on beta distributions, and you'll see this formula, y to the alpha minus 1, 1 minus y to the beta minus 1 over b of ab. And you'll also see an expansion for b of alpha beta. I said b of ab, I mean b of alpha beta, in terms of gamma functions. So that's the expansion of b. And so since that's in the denominator, I flipped that over when I pulled it outside of the denominator here. So here my alpha and beta were 2. I was given that in the problem. So I plugged those in. I got exponents of 1 on both of those. And to find those values of gamma, I just remembered that gamma of a whole number n is equal to n minus 1 factorial. So gamma of 4 is 3 factorial. That's where that 6 came from. Gamma of 2 is just 1 factorial. So both of those dropped out. And if I multiply the y through, I get y minus y squared. And so if I now try to solve u equals h of y to find the inverse function, the convenient way to write that was y plus 1 squared. And then I wanted to solve it for y. So I took the square root of both sides. Root u equals y plus 1. So y equals root u minus 1. Now I've solved for y in terms of u. So that right there, let me see if I can write that a little more cleanly, is h inverse of u. And so that's kind of the key ingredient to our transformation formula. So this is the generic transformation formula that I gave you on the introductory slides to this lecture. So that's the generic transformation formula. I dropped the H inverse of u in here, but that was in f of y, so I plugged it in here. That's where I got my 6. This right here is y. That's coming from that y. This right here is y squared. But I'm plugging in y equals h inverse of u into both of those. And then my derivative of h inverse of u is how I got the 1 over 2 root u. And I got that by taking the derivative of this right here. Remember, of course, when you take the derivative, the 1 drops out, so we just get 1 over 2 root u. And this got a little messy, but it was just algebra from here. So I expanded out my perfect square, a squared plus 2ab plus b squared, and I combined terms as best I could. I distributed the 3 over root u. Well, I didn't distribute the 3, but I distributed the root u into the parentheses, and so I got something a little bit nicer, but still not that nice. The way I got the range for u was I remembered that the range for a beta distribution is always y goes from 0 to 1. And so I took those values of y and I plugged those in to my function for u. So u is y plus 1 squared. That's how I got u goes from 1 to 4 when y goes from 0 to 1. So that's where my range of values for u comes from. So that wraps up example 6, and that's the last example for this lecture on the method of transformations. Remember, this is part of a 3-lecture series. These are all different methods for how to find the density and distribution functions for a function of random variables. This was the middle one. This is the method of transformations. In the previous lecture, we covered the method of distribution functions, and I hope you'll stick around for the next lecture, which is the method of moment generating functions. It might be worthwhile to review moment generating functions before you jump into the next lecture. So this is all part of a larger chapter on functions of random variables, and in turn, that is part of the probability lectures here on Educator.com with your host, Will Murray. Thanks very much for joining me today. Bye-bye.